You know that feeling when you follow all the rules of software architecture? I mean, you build something that's perfectly clean, super maintainable, only to watch it struggle under real pressure? Well, today we're going to dig into the hidden costs of doing things right and explore why our best intentions can sometimes lead to our biggest bottlenecks. And this quote, wow, it just gets right to the heart of the whole problem, doesn't it? It highlights this fundamental tension. What we're all taught is the correct way to build things might actually be the opposite of what delivers the best performance in the real world. So, what did these correct systems look like? Oh, they were beautiful. I mean, masterpieces of software design. You know the type: perfectly layered, elegant abstractions, following every single solid principle right down to the letter. These were the kinds of systems that you'd get a standing ovation for in a code review. Right. So where did it all go wrong? This is the big mystery we're going to try and solve. If the architecture was so perfect on paper, why did it totally fall apart when it mattered most? The answer, it turns out, is in all these hidden costs we're about to uncover. So how in the world did we even get here? To really understand the problem, we first have to appreciate why these principles became the gold standard to begin with. The promise of solid. I mean, you can see why it's so compelling, right? Every one of these principles offers a really clear benefit. One makes your code clearer, another helps with scalability, another with maintainability. It's this powerful toolkit for taming complexity, and honestly, that's why it became such a huge industry standard. And pretty soon, following these rules became a kind of badge of honor, a sign you were a real professional. But here's the crucial thing we often forget. These are guidelines, heuristics. They're not laws of physics. They're about how we organize code in our heads, not how a computer actually runs it. And confusing those two things, well, that's where everything starts to go off the rails. Okay, so let's get specific. It's time to talk about the hidden performance tax that you might be paying for that beautiful, pure architecture. So the first major cost comes from something called indirection, and it's actually pretty simple. Instead of your code just directly calling the function that does the actual work, it calls an interface or some other abstraction, which then calls the real function. It's like putting a middleman in your code's execution path. Just look at this diagram. This is the journey of a single, simple request in a typical layered system. You see how it doesn't just go straight to the database? No way. It has to hop through a controller, then a service interface, then a concrete service, a repository interface, and then the concrete repository. Every single one of those arrows is another layer of indirection, adding a tiny but very real delay. And those tiny delays, they add up. We're talking about an extra 15 to 25 milliseconds of latency before your code even starts doing anything useful, like hitting the database. This indirection also makes it way harder for the JavaScript engine to optimize your code, which means higher CPU usage. And all those little temporary objects you're creating to pass data between layers, well, the garbage collector has to clean them all up, and that process can introduce its own stutters and performance hiccups. And here's the real kicker, the pure irony of it all. We pay a guaranteed performance penalty today for a future flexibility we might never even need. We are slowing down every single request just to prepare for some what-if scenario that might never happen. So what does this look like when the rubber meets the road? Let's dive into a case study of a Node.js service that was a perfect, shining example of clean architecture right up until it hit real production traffic. So, picture this, a Node.js service built exactly how you'd think. It's a textbook-perfect layered architecture, and it's doing pretty well, handling a solid 2,000 requests per second. On paper, this thing is a total success story. But then, the traffic spikes hit. The team had planned for a P99 latency of about 80 milliseconds. Now, P99 is basically the experience of your unhappiest 1% of users. But look at what actually happened. A whopping 160 milliseconds. The latency for their most frustrated users had literally doubled. So they dug in to find out what was going on. And the culprits, well, they were the exact same hidden taxes we've been talking about. The JavaScript engine couldn't optimize the code because of all the layers. The constant creation of little data transfer objects was hammering the garbage collector. And trying to debug an error through a dozen layers of a stock trace, it was an absolute nightmare. So how do we avoid falling into these traps? It really requires a different way of thinking, what we can call the senior engineer's calculus. You see, on one side, you've got the pure architect. They're asking, is this perfectly maintainable? Is it flexible? But on the other side, you've got the senior engineer who's living in the messy reality of production.
They're asking different questions. What does this actually cost under load? How much CPU is it going to eat? And for the love of God, can I figure out what's wrong when it breaks at 3 a.m.?
And this isn't just some philosophical debate. The real-world impact is massive. In one case, a team decided to just collapse 2 layers of abstraction in a really critical part of their code. The result? They saved 60 seconds of CPU time, every single second, across their entire server fleet. That is a huge win, not just for performance, but for the company's bottom line.
And this brings us to our final and, I think, most important section. What does true engineering maturity actually look like? It's not about abandoning our principles. It's about learning how to price them.
So, how do we put this into practice, like tomorrow? Well, you start with measurement. Before you add that new shiny abstraction, measure its performance impact. Profile your code to find real hot pads, not just the ones you think are slow. Design for the changes you know are coming, not the ones you imagine might come someday. And just be ruthless about simplifying your most performance-critical code. You've got to remember this. Your beautiful architecture is a hypothesis. Your performance metrics? That's the cold, hard data. And when the data contradicts your hypothesis, you have to be willing to change your hypothesis. The numbers just don't lie. And this, right here, is what it all boils down to. True engineering maturity isn't about just throwing all the rules out the window. It's about developing the wisdom to know when to apply them. It's about understanding the trade-offs and recognizing that point where the cost of a pure abstraction is just no longer worth the benefit. So, as we wrap this up, I want to leave you with this final thought. The mark of a truly great engineer isn't just knowing the principles, it's knowing their price. The price in milliseconds, in CPU cycles, and in those late-night debugging sessions. So the question you should be asking yourself is, what is your architecture actually costing you?